Hello, this is Professor Kuehn, and welcome back to my lectures on space, time, and motion, where we are exploring Einstein's theory of special relativity. You might remember that in my last few lectures, we talked about time dilation. This is one of these consequences of accepting the two axioms, the principle of relativity and the constancy of the speed of light. You might recall that when we were talking about time dilation, we considered how time is measured using a specific kind of clock, a light clock, and how an observer who watches this clock ticking will measure a certain time interval between ticks, and another observer who sees the clock rushing by at high speed will measure a different, longer time interval between those ticks of the light clock. And then we drew some rather sweeping generalizations that this is not an artifact or a consequence of the particular clock that's being used. Rather, this has implications for how time generally is measured. And you may or may not be comfortable with those kinds of generalizations, but that's precisely what Einstein did. Now, we're going to look at one of the next features of special relativity, that is relativistic length contraction. Once again, we're going to look carefully at how length measurements are done by observers who are in motion relative to one another, and then we're going to draw some sweeping conclusions about the nature of length and the nature of space more generally. So let's talk about relativistic length contraction. So the question we're going to ask is, first of all, how is the length of an object measured? How is the length of any object measured? So we're asking a specific question about techniques for measurement. So there are two perfectly valid ways or techniques of length measurement. And what I'd like to do is describe both of these ways. So the first way, I'll call it method number one. This is the one with which you are probably most familiar. This would be, let's suppose that you wanted to measure the length of, let's say, the desk at which you're sitting. How do you measure the length of it? Well, you take a ruler that's of a known length, let's say a 1-foot ruler, and you lay the ruler on the desk. Maybe you lay several rulers on the desk end to end, and you count how many rulers fit on your desk. If there are 3 rulers that fit on your desk, then your desk is 3 feet long. Notice what you're doing there. You are placing a measuring rod, as Einstein would call it, a measuring stick, a ruler, in the same frame of reference as your desk and counting how many of them fit. So let's describe this. An observer at rest with respect to the object under consideration, so the object to be measured, places a stationary ruler along or against the object. Okay, so this is a very typical way of measuring the length of something. Okay, and this is non-controversial. That's method one. But if you think about it, there is another method that people typically use to measure the length of an object. Let's suppose that you are, in downtown Wauwatosa, where we live, sitting at Cafe Hollander, and you're sitting with your friends, and a train passes right by along the train tracks. And you were to want to know how long that train is. Well, one way to do it would be jump aboard the train and place a measuring tape along the train from the back to the front, but that would involve you jumping onto the train. That might be a hassle. So there's another way to do it. Let's suppose you knew that the train was traveling at 60 miles per hour. And you had a wristwatch on your arm. You could quite easily measure the length of the train. How would you do this? You would start your stopwatch right when the engine passes you, and you stop the stopwatch the moment the caboose passes you. And by knowing the speed of the train and the time that it took to pass you, you could deduce the length of the train. So if we were just to use some simple numbers, this is a bit unrealistic, but if the train was going at 60 miles per hour and it took, let's say, a half an hour to pass you, you would conclude that the train is 30 miles long. I know that's a long train, but you get the point. By measuring the time and knowing the speed, you can do a perfectly valid measurement of the length of that train. So let me write this down. So an observer in this method, an observer who sees the object under consideration, the object that is to be measured, in this case it would be the train, who sees the object to be measured rushing past at a speed v, we'll call it, measures how much time elapses between when the front and back of the object passes his or her location. Okay, so these are two perfectly valid ways of measuring the length of an object. Okay, so let's do this in a particular example. Okay, so let's do an example here. Let's suppose, and we'll use, Luke and John once again, because those are my favorite characters for these kind of discussions. So let's suppose that Luke is riding on a train. And it's rushing past John at speed v. Maybe John is at Cafe Hollander. So the train is rushing past John at a speed v. Okay, now of course, it's good to step back and think about this for a moment. Luke will consider the train to be at rest and John moving past him at speed v, and John will consider himself to be at rest and Luke on the train is rushing past him at speed v. So they agree on the relative speed of the train, that is of Luke and John, but they disagree about who's in motion and who is at rest. So it's just good to keep that in mind. Okay, and let's suppose that Luke, who is at rest with respect to the train, so he's at rest with respect to the train, let's suppose he has a long tape measure and he measures the length of the train using method 1. So he measures the train length using method 1 because he's at rest compared to the train, and so is his meter stick, to be, and let's just make up a number here, 10 meters long. It's a short train. So the length of the train, according to Luke, is 10 meters. Okay, so that's the length of the train according to Luke. Now, what about John? What would be the length of the train according to John? Well, John sees a train rushing past at speed v. So he watches from his seat at Cafe Hollander the train rushing by at a speed v, right? And what he's going to do is he's going to measure the interval between two events. The first event would be the front of the train passing his location, and the second event would be the back of the train passing his location. So he measures the time interval between event 1, which is the front of the train passes him. Sorry, my handwriting is not great here. And so that's event 1, and event 2 would be the back of the train passes him, or passes his location. Okay? And then what he does is he uses this method 2, which I mentioned a moment ago, to find the time interval, delta tj. So the time interval between these events is what he measures, delta tj. That's the time interval that John measures between event 1 and event 2. And then how does he compute the length of the train? He deduces, or he concludes, that the length of the train is the length, according to John, would be the speed of the train times the time interval between those two events according to John. Okay? Now, here's the question. I hope that makes sense to you so far. Now, here's the question I want to ask. Does the length of the train according to John equal the length of the train according to Luke? So do they agree on the length of the train? So notice, like I said, we could ask Luke about the time interval between event 1 and event 2. So they both agree that the train and John, that John passes the front of the train and John passes the back of the train. From Luke's perspective, what happens is John is rushing past, John passes the front of the train, and John passes the back of the train. And he could measure the time interval between those two events. From John's perspective, the front of the train passes him, and then the back of the train passes him. Those are the two events, okay? So let's find the time interval between those two events as measured by Luke. So the time interval as measured by Luke, again, these are the same two events, they just disagree about who's moving and who's not, is the delta t according to Luke would be the length of the train as measured by Luke divided by the speed of the train. Okay, right? So he knows the length of his train. He knows, from his perspective, it's the speed of John. So he knows the length of the train. So let's kind of draw this from Luke's perspective. Luke is here on the train. He knows the length of the train. That's the length according to Luke. And he sees John, who's sitting there in the cafe, going at some speed v past him, right? And the first event would be when John passes the front of the train. The second event is when John passes the back of the train. And if Luke knows the length of the train from his perspective and the speed of John, he could figure out the time interval between those two events. Okay? And now what we can do is we can say, what is this time interval between those two events as measured by Luke compared to the time interval between those same two events as measured by John? And that would be connected by the time dilation formula. Okay, so this is by the time dilation formula that we developed in the last lecture. Okay, delta t Luke is going to be equal to gamma times delta t John. Oops, delta t John. Okay? Now, you might, when looking at this formula, you might think, did we assign the correct time interval? Which one is measuring delta t naught? So recall, delta t is gamma times delta t naught, right? And delta t naught would be the time interval between events as measured by someone who sees those events happening at the exact same location. So is it in fact John who is measuring the time interval between the events that are happening in the same location? And the answer is yes. Because John is sitting here at Cafe Hollander. The front of the train passes him, that's event 1. That's at a particular coordinate in his particular x location in his coordinate system. And then the back of the train passes him. That's at the exact same location in his coordinate system. So here, John, who is sitting outside, is the one measuring the proper time, or delta t naught, between those two events. Luke is measuring the time interval between the same two events, but they're not happening at the same location. He sees John pass the front of his train and then pass the back of his train. Those two events are happening not at the same spatial location. Okay, so just so we make sure that we have that formula set up correctly. Okay, so again, John is measuring delta t naught. Now notice we have two formulas. We have this formula right here, connecting the time intervals between these two events. And we also have these formulas right here and here. And what we're going to do is we're going to combine these formulas to get a relationship between the lengths as measured by these two observers. So combining these formulas, or these formulae, we get the length according to John is equal to the velocity times delta t according to John. That is this formula up here. I'm just rewriting it. Okay? And that is going to be equal to the velocity times, well, what's delta t according to John? It's going to be delta t according to Luke divided by gamma, right? And that is using this, I'm rearranging this formula right here in order to get solving for delta t according to John and plugging it in. Okay? And now what I can do is I'm going to factor out the gamma, 1 over gamma, times the velocity times delta t according to Luke. Okay? And now I have the length according to John is equal to what? Well, the velocity times delta t according to Luke is just equal to the length according to Luke. So that's going to be equal to 1 over gamma times the length according to Luke. And now I have used this third formula right here. So I'm basically using this to get that. So the length according to John is equal to the length according to Luke divided by gamma. Okay? And notice that gamma is bigger than 1, as always. And so if you have a larger than 1 number in the denominator, this factor, 1 over gamma, is going to be less than 1. And so the length according to John is going to be less than the length according to Luke. In other words, John measures that the train is shorter than 10 meters. So John measures that the length of the train is less than 10 meters, right? That's what we've arrived at. Again, you might be a little bit uncomfortable with the calculations we've done. If you're uncomfortable, you can go back through and look at how we did this. We haven't really made any preposterous assumptions here. We've simply used method 1 and method 2 for measuring the length of an object. And then perhaps the more controversial thing is we've used the time dilation formula to connect the time intervals between events as measured by observers who are in motion relative to one another. And the upshot of that is that the length of the train is shorter as measured by John than by Luke, who's riding on the train. In other words, and this is what we call relativistic length contraction, a moving object is shorter than a stationary object. Both observers are measuring the length of the train. They both have valid measurements of the train, and Luke, who's riding on the train, who sees it at rest, measures 10 meters, and John, who sees it rushing past, measures less than 10 meters. We could figure out how much less if we knew what the speed of the train was. And so we'll talk a little bit more about that in the next lecture.